So we are going to learn what are metals and non-metals. So these, whatever you're able to see on the screen, that is the difference between metals and non-metals. But generally, what is a metal? What is the very definition of a metal, or what is the very definition of a non-metal? So metals are nothing but elements which have the tendency to lose electrons. We have different types of elements, and in each element, the nucleus is attracting the electrons towards itself, which are revolving and all of that. So some of the elements will have an ability or will have the tendency to give away the electrons or lose the electrons, and those are called metals. And some other elements will have the tendency to gain electrons, and those are called as non-metals. So metals will lose electrons and non-metals will gain electrons under some circumstances. So that is the very idea of a metal and a non-metal. Given an element, if it has the ability to give away the electrons or donate the electrons or lose the electrons, then it's called as a metal. Or if it has the tendency to gain or capture electrons, then it is called as a non-metal. Now, what we are able to see on the screen is the difference between the properties of metals and non-metals. Like what is the behavioral patterns of metals and non-metals. So metals are good conductors of electricity and heat. So they can really conduct electricity and heat well. And that is why metals are used in electrical transmission, for example, copper. And also metals are used in for cooking also. In cooking utensils also we use metals. For example, aluminium is used as vessels, or steel is used. Steel is an alloy of a metal, so of some metals, and likewise. So since metals are very good conductors of heat and electricity, they can conduct electricity and heat like anything. They are used in electricity transmission and also to provide heat or to conduct heat. Non-metals are bad conductors of heat and electricity. That is why handles of kitchen utensils, the plastic handle, that is a non-metal, and also the insulation of electrical wires, that is also a non-metal, for example, rubber. So likewise. So the second point is metals are malleable. So malleable means they can be beaten into thin sheets. You can actually beat the metals with, when you apply some pressure, they can be made as thin sheets. And metals as sheets, we use them in some music instruments. Sometimes we have the outer boundary of a drums. So that is basically made of a metal sheet or something. So likewise, metals are used as the discs that are used in playing drums. That is also a metal sheet. So likewise, or the plates that we eat, sometimes we eat with a metal plate, and that's also the property that's called as malleability, or it's called malleable. And non-metals are non-malleable, which means they cannot be beaten into thin sheets. So this is something that we need to understand. And if a metal can be made in the form of a wire, if they can be drawn in the form of wire, if they can be made in the form of tubes and wires, then it is called as ductile. That property is called as ductile. And because of this property, metals are widely used in bicycles, in the wheels and all. We can see this, the forks wires are basically made up of metals. Also, they are used as necklaces and chains and bracelets. That is because they have the ability to be made in the form of wires. Non-metals cannot be made in the form of wire. They cannot be made thin, or they cannot be rolled to a thin state, and that's why they are non-ductile. And also metals are sonorous, which means they will be able to produce a striking sound or a ringing sound when we hit them. Basically, all the string instruments, most of the music instruments which are the strings of violin and guitar, they're all made up of metals, which can be actually, when we strike them using something, we'll be able to hear a ringing effect or a sound which kind of echoes. That is what is meant by sonorous, and that is why metal bells are used. So the bells that we use to ring in our houses or in our temples and all of that, that is made up of metals. And also sometimes the bells that we have in the school bells are also made up of metals. Because of this property, non-metals are non-sonorous, which means they can't produce a ringing sound. The next one is metals have a high tensile strength due to high attraction between the molecules. So the atoms are very tightly packed in the metals, and they will be quite strongly held among themselves, which gives them a very high tensile strength, which means they are quite strong in their nature, quite rigid, and it's not so easy to stretch them or to expand them. So that is the meaning of this word. And also non-metals have low tensile strength, which means they can be kind of easily stretched as compared to metals. That is also because the atoms are not so bonded when it comes to non-metals. Metals have high density, which means there is a lot of atoms and molecules within a particular space. And non-metals have low density for the same reason. And metals have high melting and boiling point. The reason, so also when it comes to this point, because it has a lot of strength, metals are used in very important structures, like for example, construction of bridges, construction of flyovers, we use metals, construction of ships, we use metals. That is because they have very good strength. Because they have high density also, we use them in construction for grill gates and all that. Metals have high melting and boiling point, which means it takes a lot of temperature, a lot of heat to melt them, also to boil them. So that is why they have a very high melting and boiling point. This is also because they have high attraction between the molecules, and non-metals have low melting and boiling point. This has been wrongly written. This is supposed to be non-metals. Yeah. So non-metals have low melting and boiling points. And the last point is very important, especially with respect to this chapter. Metals combine with oxygen to form basic oxides, and non-metals combine with oxygen to form acidic oxides. So what we mean by this is metals will be able to react with oxygen and they will form basic oxide. Let me give you an example. For example, magnesium reacts with oxygen to form magnesium oxide. So let me balance this. So this is the reaction. So this is the reaction for formation of magnesium oxide. So now when you look at this particular reaction, magnesium reacts with oxygen to form magnesium oxide. The oxide that is formed is basic in nature. So what do we mean by basic is, when we add water to this, it will become a base. It will become a base, which means bases have OH minus ions. It will behave as a base or an alkali. That is why this is called as a basic oxide. I repeat, metals like magnesium. So magnesium is an example of a metal. So it is reacting with oxygen to form an oxide which is basic. So metals always give basic oxides, which means the oxide that we get from a metal will be able to behave as a base in future when we dilute it with water or something. They will be able to form bases, which means they will be able to liberate OH minus ions in future. And non-metals combine with oxygen to form acidic oxide. This is quite obvious and clear. An example for a non-metal is sulfur. So as we all know, sulfur reacts with oxygen to give sulfur dioxide. And this is a very important gas that we have dealt in acid rain and greenhouse effect, global warming and all of that. So sulfur is a non-metal. It reacts with oxygen to form sulfur dioxide, which is an acidic oxide. And that is why it is causing acid rain. When it gets mixed with water, it becomes sulfuric acid. So it behaves like an acid, whereas the metallic oxides will behave like a base. So apart from the properties that we saw in the tabular column, there is one more property for metals, which is metals are lustrous, which means they can shine, they give a shining effect, and non-metals are non-lustrous, which means they don't shine. Now, there are exceptions in certain properties. We are going to look at the exceptions. The first point is all metals except mercury exist as solids. We know that all the metals are solids. We saw a point where it has a high tensile strength, it is rigid, it is dense, it has a high density, which means all the metals are solids except mercury, which is the liquid at room temperature. Room temperature in the sense, under normal conditions, mercury is a liquid, but all other metals are solids. So you may get a question like, which is the liquid non-metal? Sorry, which is the liquid metal? So you'll be writing the answer as mercury, because all the other metals are solids. Now, then why do we have it under metals? Is because mercury will be able to satisfy the other properties of metals. Like for example, it may be able to give away electrons or something like that. And also it gives a shining effect. So again, it is in line with the property of a metal. So that is why, and because of this property of mercury, because it is a liquid, we can easily use it in thermometers so that it can easily rise and come down because it's a liquid. So we are making advantage or making use of this property of mercury. Okay. So the next one is metals. We also saw a point where metals have very high melting and boiling point, which means it is not easy to melt a metal. If you just keep an iron rod under fire, it is not easy to melt it, except gallium and cesium. So gallium and cesium are two metals which can melt so easily. This is also an exception. So all the metals have high melting and boiling points except gallium and cesium. They have quite low melting points. They have very low melting points to an extent that when we keep them on our palm, they melt. Like for example, when we pour nail polish remover or sanitizer in our palm, as soon as we pour it, it automatically gets evaporated, volatile. It melts. So like by using the heat from our palm, likewise, for gallium and cesium, the heat in our skin in the palm is very much sufficient to melt it. So it has so much of, so low a melting point it has. So this is also quite important when it comes to exceptions. And iodine is a non-metal, but it is lustrous. So iodine comes under non-metal category for other reasons, but it is still lustrous, which means it can shine. And this is a very important point. The third point is carbon is a non-metal. We all know carbon is a non-metal, and carbon can exist as different forms. And that is why there is a separate chapter dedicated for this, the next chapter, which is called carbon and its compounds. So the different forms of carbon is called as an allotrope. So for example, diamond is an allotrope, graphite is an allotrope, coal is an allotrope of carbon, coke is an allotrope of carbon, and likewise. So which means they are different forms of carbon. So if you look at diamond, diamond is not an element. It's a form of carbon. When carbon is so hard and so strongly bonded, then it's called diamond. When carbon is softly bonded, then it is called as graphite. So depending upon how the carbon atoms are bonded, structurally, we have different forms of carbon, and one of them is diamond. So though diamond is a allotrope of carbon, basically carbon is a non-metal. So it should not be shining, but diamond shines like anything, as we know. So this is also an exception. So diamond is an allotrope of carbon, which is a non-metal, which means it should be soft. It should have low density, but it is the hardest substance on earth, as we all know. It is the hardest natural substance when it comes to diamond. But in general, non-metals are not hard. They are quite soft and tender. But diamond, though it is a non-metal, it is hard. And also diamond has a very high melting point, but it is a non-metal. It should have a low melting point, but it's an exception. Likewise, graphite is another allotrope of carbon and is used as a conductor of electricity. It's a very good conductor of electricity, but it is not supposed to be because it's a non-metal, but it's an exception. Graphite is also a very good conductor of electricity, except all other non-metals are poor conductors of electricity. So this is something that we need to know. And the fourth point is alkali metals. What I mean by alkali metals is, if you look at the periodic table, whatever is there in the first column, all those are called as alkali metals. Lithium, sodium, potassium, and all of them. Why they are called as alkali metals is because when their oxides are mixed with water, they will be able to form bases. For example, sodium is sodium hydroxide. Potassium is potassium hydroxide. You can see these are all bases, OH minus ions. That is why they are called as alkali metals. And these alkali metals, though they are metals, they don't follow that hardness. They are quite soft and they can be easily cut with a knife. They are so soft that you can cut them like cutting a cake. So they have very low density and low melting point. Even though they are metals, they have low density. They are supposed to have high, but they have low densities and low melting points for their reasons, because of their structure, because of the way they are bonded, and various reasons. So these are the anomalous behaviors or exceptions of properties of metals and non-metals. Now we are going to see what happens when metals are burnt in air. So what do we mean by burning is, sometimes we need to give an external supply, like a Bunsen burner or some form of heat, in order to make a metal burn in air in the sense along with oxygen. Sometimes they can readily catch fire even without supply of heat. So there are different metals will behave differently when we burn them in air, and we are going to see how they behave based on their based on the different types of metals. So as we all know, this is a general format. metal reacts with oxygen to form something called as a metal oxide. For example, sodium reacts with oxygen to form sodium oxide. Magnesium reacts with oxygen to form magnesium oxide, and so on. So the example that they have given is copper. As you can see, copper reacts with oxygen to form copper oxide. And this copper oxide is a black color oxide. It is black in color. So that is that's an observation with which we can find whether it's copper oxide or not. So copper reacts with oxygen to form copper oxide. Aluminium reacts with oxygen to form aluminium oxide. Likewise. Now we will have a separate session to understand why there is a 2 here, why there is a 3 here, and why this 2 is not coming here. Rather, it has been put as common. Now, all of this we'll have a separate session to understand how valency works and all of that. Now, a very important thing is we just saw some time back that metal oxides are basic in nature. And we also saw non-metal oxides are acidic in nature. For example, here copper oxide is a metal oxide because copper is a metal. And aluminum oxide is also a metal oxide, which means they all will behave like bases. That's why it's called basic in nature, whereas non-metal oxides will be acidic in nature, as you all know. Now, a very important question from examination point of view is what is meant by amphoteric oxide? A very important question. So this is the definition. Metal oxides which react with both acids as well as bases to produce salt and water are called amphoteric oxides. And these two are the reactions for amphoteric oxides. And these are the examples, aluminum oxide and zinc oxide. These are other examples for amphoteric oxides. So some metal oxides will react with acids. Some of them will react with bases, and there are some others which will react with both acids as well as bases. So those oxides are called, those metal oxides are called amphoteric oxides. And one more such example is zinc oxide. If you look at the reaction, we have taken aluminum oxide and it reacts with HCl, which is an acid. It reacts with base also, sodium hydroxide, to give respective salts. The first salt is called aluminum chloride and the second salt is called sodium aluminate. So this is called amphoteric oxides. Now, what happens when we dilute the oxides in water? What happens when we add water to the oxides? They become hydroxides. If you add water to oxides, they become hydroxide, and that is the next one. You can clearly see sodium oxide, when you add water, it becomes sodium hydroxide. Potassium oxide with water, it becomes potassium hydroxide. So basically, these two are bases because they have OH minus ions, and that is why they are called as basic oxides in the first place. This is something that we need to know. Now, this paragraph summarizes the behavior of different metals with oxygen or with air, how they react, whether they react vigorously, whether they react readily, or they react slowly, or they will never react. To understand this and also to relate this, let us try to look at the reactivity series and then come back to this. So I have shown a mnemonic to understand the reactivity series. So the reactivity series is basically a series of elements which have been arranged in a particular order of reactivity, which means potassium, sodium, calcium, whatever we're able to see at the top, they are very reactive, and whatever is at the bottom, they are less reactive. So in this manner, we can compare any two elements, for example, magnesium and lead, and we can say magnesium is more reactive. And this idea can also be used in understanding displacement reactions in unit 1. So magnesium will be able to displace lead from its solution or something. So to memorize this, we have a mnemonic which is please stop calling me a careless zebra, instead try learning how copper saves gold. And using this mnemonic, we can actually understand the reactivity series. So this reactivity series is very important. So I have listed down the reactivity series in the left-hand side, just the symbols. So whatever is there at the top is most reactive and whatever is there at the bottom is least reactive. Now with this understanding, if you look at how different metals will react with oxygen, we can clearly see metals such as potassium and sodium react vigorously, which means whenever we bring oxygen near to the potassium or sodium, they can readily catch fire. They will immediately catch fire and they will react vigorously. This is about potassium and sodium. So I would like to mention this as vigorous. So they will be able to vigorously catch fire, the first two. This is something that we need to know. So when we keep them in open air, like for example, pure sodium metal or pure potassium metal, when kept it in open air, it can catch fire and will become a disaster. For that only, to protect them, we are keeping them in kerosene oil. We always store them by immersing them in kerosene oil. And why we use kerosene oil is because sodium or potassium doesn't get dissolved in kerosene. So you can readily take it off. And that is the main reason they are stored in kerosene oil. So this is very important. So they can readily catch fire. For that reason, they are not kept in open containers. They are kept in immersed in kerosene oil. They can make use of it later. And then other metals which are little downward in the reactivity series. If you look at it, magnesium, aluminum, zinc, and lead. So magnesium, aluminum, zinc, and lead. Maybe I can include iron also. They have a little bit of an oxide layer around them. These metals will have a layer of oxide because they have been exposed to air and they will already have an oxide layer. So this will prevent further oxidation, which means this will prevent them from burning readily. And because of which they don't readily catch fire. Of course, they can be burnt, but not as vigorous as potassium or sodium. That is very important. So this is about these three metals. That is about magnesium, aluminum, zinc, and lead. So with respect to these four, we can write the hint as have an oxide layer already. So they already have an oxide layer. For example, any of these metals, aluminum, when it is in atmosphere, in contact to the atmosphere, it will be able to form an oxide layer surrounding it, which will prevent it from further oxidation. There is already an oxide layer, so it will not readily catch fire. But when we keep on burning it, the oxide layer will be removed and it will also start to melt or burn. And with respect to iron, it behaves a bit interestingly because iron rod will not burn, but iron fillings can burn. Fillings in the sense powder form. If iron is in the rod form, it cannot burn, but if it is in the form of powder, it can easily burn, and because of the change in structure and all of that. And copper does not burn. So others will not burn, as you all know. Copper does not burn. And it will also form an oxide layer. Silver and gold also will not react with oxygen. So what we're able to see here is as we keep going down the reactivities, it's very clear that the reactivity decreases. Therefore, the ability to react with oxygen is also decreasing. As you keep going upwards, you can see that they're reacting so much. As you keep going down, slowly the reactivity with oxygen is also decreasing. And the same concept we're going to use to learn how they react with water also. So this is something that we need to know.
Thank you.